probably for all my faithful fans in Uganda. So they continue to get all their physics updates. So the first thing I want to really throw out there in front of you guys is this is the function that describes the acceleration of the skier. Now, I think a lot of students are thrown off by this, a lot. And from the moment they see it, they wither. But it's more than just that. This function exists only from time 0 to time capital T. And after that, the acceleration is 0 for every point after that, which means the velocity increases and then it stays constant when I make it to time capital T. But a lot of people they see this formula and it really, really throws them. And the question, part A asks, derive an expression for the velocity of the skier as a function of time during the acceleration and assume the skier starts from rest. So derive an expression for the velocity. You should know how to do this. Even if you don't know how to complete it, you should know where to start. Shreyas? What's that? That's exactly what I would want you guys to be able to do. The first thing you should recognize is that you have an expression for the acceleration as a function of time. So the first thing you should do is you should change acceleration into dv dt. And although last time we've I hope gotten away from just saying take the antiderivative, although that's exactly what you're going to do, I want to start moving us towards understanding that we're going to replace acceleration with dv dt. And the reason is quite simple. If they see you do that, that's probably a point. If you just start taking the antiderivative, they won't know that you understand that it's equal to dv dt, especially for this one, which means you should do this, and you should do something more than this. You should split the derivative. You should take the integral of both sides. These are all things we've talked about. Therefore, my belief is that you should be able to do these even if you don't fully understand all the things that you're doing. And you should set your limits. At time 0, the velocity was 0. That's what they said. It started from rest. At time t in the future, it's at some v in the future. Now this, the part on the left, I think you should be able to do, because that's just 1. There's the implied 1 here. So my expectation is that the left side is going to be v minus 0. And you can take the antiderivative of 1 with respect to v. I don't want to go through all of that. If you don't know why that's there, we have trouble. The right side, on the other hand, it might be too much for you. I know it's too much for almost everybody so far today, but it might be too much for you when you actually take the exam too. So first, let me ask, how many of you are in BC right now? Keep your hands up if you were in AB last year. So I've got 3 people who should be able to do this. But I also know, and I'm pretty reasonable about this, I think that learning might not have been as solid last year. So maybe you don't remember. Now, what has to be done from this point forwards actually is a lot. And although I want you to see it, there's a reason why I want you to see it. You will eventually be able to do this with no trouble at all, whether you're in AB or BC. The process is simple and is one of the more basic things you do in calculus. But for right now, it's going to look like voodoo because you've never done it before. And you're just going to have to trust me in that I expect you to make it to this point right now, every single time. If you're asked to find an expression for the velocity and you've been given an acceleration, you should turn it into a differential equation, split that differential, and get 2 integrals. You should be doing that at this point. We're not doing a lot of practice of that because we have to stop right here. But I don't want to stop here. I want you to see the answer. So we're going to go forwards with this, but expect that you might be able to follow it, but I'm not teaching you how to do it right now. I'm just telling you what comes next. And what comes next is us focusing on this side. We're going to pull the A max out. That's just some max acceleration. And then we're going to look inside this derivative or this integral. And by look inside, what I mean is we're going to look at exactly what we've been given. We have sine of pi over t times t with respect to t. So this is a function. This is the function of sine, and there's my t is inside here. Now, you probably have heard by now that the antiderivative of sine is negative cosine. You should have heard that because we said it in class. So you know that the antiderivative of sine is negative cosine, and the antiderivative of cosine is sine. It should be in your notes. It's been discussed. I don't give it to you as a question, but this isn't sine. This is sine of another function that has t in the function. What I mean by that is if I gave you sine of theta d theta and ask you to take the integral of that, you could do this. You could write this as minus cosine theta. Just throw that wherever. But you don't have this. You have a function inside here. Now, you guys who have AB right now, you should probably be coming to grips with the idea that sometimes you have more than one function, meaning you might have sine of 6t and be asked to find the derivative of this. Because I know that you guys are doing derivatives. And you should have done the derivative of this so far. You would have used something called the chain rule, which means you would take the derivative of sine and get cosine of 6t. Then you would multiply by the derivative of whatever was inside here. The chain rule. Well, what we're going to learn is the version of the chain rule for integrals. And it's called U sub. U sub is how you do the chain rule when you have a function inside a function. The difference is that when you're taking a derivative, the chain rule always works, period. In fact, I don't even learn all the other rules because the chain rule does so much. U sub doesn't always work. So, and when U sub doesn't work, you'll know it because it doesn't give you something that's easier to solve. It gives you something that's more complicated to solve. That's when you know U sub failed you. You'll have to find some other method. But U sub is going to work here. Why? Because I chose one that I knew it would work. So what U sub is really straightforward. You create a function that you believe through substitution will make your function simpler. I'm going to U sub all the stuff that's in the parentheses. Now, you can't just do that because the stuff in the parentheses is with respect to t, so we have to get rid of this dt as well. So to do that, the first thing we're going to do is take the derivative of our function for u with respect to t. Again, you know how to take derivatives. So pi over t is just a constant. So this derivative with respect to t is just pi over capital T. I'm pretty confident you know how to do that, but people earlier today thought that looked weird. Are we good with that? Now you need to solve this for dt. And by cross multiplication, that's what you get when you solve it for dt. So u sub means I'm going to substitute in for my function, and I'm going to substitute in for dt. So when I do, I get a max integral sine of u. And then I have this t over pi times du. Now, if your u sub works, whatever you just subbed in, whatever this is a constant, and you should be able to take it out of your integral, or something that will make your integration okay. For us, it's a constant. So we can just take it all out front, and we're left with a max times t over pi times the integral of sine u with respect to u. U sub produced a simpler function of which we do know the antiderivative. That's your goal for U sub. Now, you still have to do the calculus. I still have to take the antiderivative. And then I still have to apply my limits. But the problem is the limits I have are for t, and they're not for u. So I have to, in the end, put back in what I substituted away, because my limits were based on t, and so was my function. Now, I'd say we're almost done, but we still have to put the limits in. So put that over there, and I'll get let's see. Oh, come on, Mr. Shelton. So we'll get v minus 0 on one side, and we'll get a max t over pi times, well, I'm going to put in t first, so minus cosine pi t over t minus, I'll put 0 in. What is the cosine of 0? 1, so minus negative 1. So that's just going to turn that into plus 1. So that just all becomes plus 1. There it is. That's the answer. That is our expression for the velocity in terms of the time. It's not easy to look at, is it? But that's what it is. Now, interestingly enough, at t equals 0, I put in 0 for t here. I'll get cosine of 0, which will make all of this negative 1. And negative 1 plus 1 is 0. So when I put in t equals 0, I get what I expected, v equals 0. But when I put t equals capital T, all of this becomes pi. What's the cosine of pi? Negative 1. So negative 1 times a negative will turn all of this into positive 1. Plus 2, I'm sorry, plus another 1 makes it 2. So v here becomes 2a max t over pi. I just put in the two extremes, because after capital T, the acceleration is 0. All right, that's question A. Now, really, question A ended right here, but testing limits is always something I suggest we do to make sure we got the right answer. But that's question A. I'm saying this because you can't do question B in this problem without having done question A. It's just brutal. In fact, the whole problem hinges on having done question A, or so it seems. Look what the next question asks. Derive an expression for the work done by the net force on the skier from rest until the terminal speed has been reached. Do I even have a function for the net force? I have a function for the acceleration, but I don't have any idea what the force is. I guess I could state that the force is equal to ma, the net force, and I could say that that's equal to m a max times the sine of pi t over t. I could do that, but I can't do anything with this. I can't multiply by dx and take the integral, because it changes with time, not position. What are they asking of me? And here's where you have to be able to persevere. What are they really saying? Can you read between the lines and figure out what they're really saying here? See, this is why we have to be able to kind of get away from that anxiety and focus on what they really want. And what they really want is the net work done. The work done by a net force is the net work, which means what they really wanted here was answer to question B. One half mv squared minus 1/2 m 0 squared. Now, if you can't do question A, you don't know that that v is going to be 2a max t over pi. You don't know that. But you don't have to. If you write this down for question B, you get all the credit for B. If you couldn't find V, and I think that there's going to be some of you who will not be able to find V even after all of this year. Maybe you'll get to some part of it, I hope. But you might not be able to do all of this. You might freeze. You might not know. What I need you to understand is that's not where you stop. You can't lose all 15 points. We've talked about the fact that they're going to hide some of these things. They're going to try and make it not easy. They wanted the net force done by, the work done by the net force. So they were asking for the net work. They wanted to change the kinetic energy. That's all they wanted. And if you can express that, you got all three of those points. After that, determine the magnitude of the force exerted by the rope at the top. You just have to say MA. That's what all you needed. There's a lot here that you can do. But question A is brutal. Of course, that's why you don't see me giving this out as a test question. I give it out as a question for us to look at so we can prepare for it if it does show up on your exam. We can't run away from these questions. And if they show up, we're going to have to find a way to acquire some of the points. There's one like this about every 4 years, a question out of left field, and it almost always involves a little bit of calculus. This one, I'd say, involves a little bit of calculus. You guys who finished AB last year should know that doing a quick U sub is actually a little bit of calculus. But there it is. It's been said before, you can't get a 5 on the exam without being able to do a little bit of calculus. So I wanted to show you this today. It goes on to talk about force. It goes on to talk about an even weirder function. But you don't have to do calculus after this. You just have to show some conversation about it. But I need you to be prepared to see questions like this. So I've got to work them in there so you can be seeing them. But here, for the rest of the day, I'm going to make it a little bit easy on you. For us to keep ourselves on task and have a test in a reasonable amount of time, I want you to realize that these kinds of calculus questions are things we can't really count on for your tests right now. But you have to be able to do them by the end of the year, which means April is going to be a time for us to see a lot of these problems again. But it's when we're going to see all the problems we couldn't do because your calculus skills weren't ready. So a lot of drills going to take place in April, and you're going to think that, why didn't we do all this earlier? I want you to remember this conversation. This is why we can't do a lot of this stuff earlier. All right? There's no calculus on the semester test, except for like simple acceleration functions. Let's talk about power for a few minutes. Power is a rate. It's the rate at which work is done. Sometimes I say it's the rate at which energy is consumed or used. But either way, it's a rate, which means it's something that happens over time. As a rate, to actually write out what power is, I have to write it as a derivative because all rates are a derivative function with respect to time. Now, what that actually means is that we're talking about how fast work is done. So when we talk about power, we're talking about a system that's doing work. We often talk about engines and stuff like that when it comes to power. That's kind of the colloquial thing. I want to be really clear about something. Power doesn't mean that you can actually apply a lot of force. Being powerful tends to have this idea that you can push or move big things. A powerful engine can't necessarily apply a lot of force. It does work quickly. It doesn't mean it applies a lot of force to an object. So don't confuse power with force. There are plenty of things that are very powerful engines that don't apply a lot of force. So if you buy a powerful engine, it might not lift what you want it to lift, but it might be able to do work quickly. So be aware that power isn't an expression for force. When you buy a powerful car, it doesn't necessarily mean that it can pull a heavy trailer. You need to look for other things about the car's engine to determine whether it's good at pulling a trailer, because that means it can apply a lot of force. So you look for like torque ratings on the engine. Torque is a measurement for how much force an engine can provide. Power is for how fast it can do work. So there is a distinct difference, and be careful about that kind of stuff. Now, we're hardly ever going to use the calculus definition, and hardly ever shows up on the exam. It's very, very seldom do they give us an expression for work that's in terms of time. So we can't take the derivative of hardly any of our work functions. Remember, work is almost always based on displacement. So we don't usually have expressions for work that are based on time. So we don't have many expressions where we can take the derivative. But at the same time, we can talk about the work done by a constant force. In fact, we can express work in terms of a constant force. And when we do, we get other ways to calculate power. So there are two ways we tend to calculate power: work over time or force times velocity. And understand, when I say work over time, I mean work over time or energy over time. So this could also be the change in kinetic energy over time. These are all different ways that power can be calculated. The unit of power is a joule per second, which has been given the name watt after Mr. Watt. So when we talk about watts, we're talking about the rate at which energy is consumed or used. In electronics, we used it a lot because we talked about the flow of electrical current, and we specifically talked about how much energy was being consumed due to the flow of electrical current. So we ended up talking about power a lot in electricity. We don't talk about power as much in mechanics, but that's not because we don't have any reason to. It's just that doesn't come up as much for us. We're more concerned with you guys nailing down how things happened, not how fast they happen. Power is a way of working in time into energy equations. So keep that in mind as well, that we tend to see the working in of time into energy equations through the use of power. But it's not really going to be a big part of the test. So footnote maybe, multiple choice from time to time, maybe a part 2 of a question C, but don't expect it to be the entirety of a question. Does that make sense? So the homework ones, they're going to refer to these kinds of questions: force times velocity, and how much work over time. Eventually, it would be nice if we could get a short expression of efficiency, because efficiency actually has a little bit more meaning. And power and efficiency are not related, but they tend to be discussed at the same time. While power is a discussion of how fast we consume energy, efficiency is a ratio of the energy we get out compared to what we put in. It's a ratio. I'm using energy very broadly. It's what you get for what goes in. So if you do physical work, it's how much useful, oops, I blew writing that. If you do physical work, it's how much useful energy you get back. So often we'll do things like we'll compare how much energy was in a gallon of gasoline, and then we'll compare it to how much useful work you got out of that system. That's an efficiency rating. And we don't have any systems that are 100% efficient. We have exchanges for energy that can be 100% efficient, but we don't have any systems that convert energy from one form to another that are 100% efficient. All right. Bye, guys. Have a nice day. You guys at home? Have a nice day.
Bye, Mr. Shelton.
Bye. If you're coming for the makeup test, you got to log out and log back in under the makeup test thing.